Hi, I will talk about the schematic of our buck converter. We have an application which it has specification for the input voltage 12 to 16.8 and the output current is 500 milliamp. So even this buck converter of course can take larger input voltage and the output current it can be up to 800 milliamp. You can design your LDO, your buck converter on a specific application. And when you do that, those values of the value of inductor, for example, will be changed. And then you have other calculation will be changed. So it doesn't mean if you have a load current of 800 milliamp, this will not work. It will work, but the performance when you make your calculation according to 500 milliamp and this input, the performance will be different if you're using 800. So you might have a more ripple current and not a very stable output voltage. So that's why you have to select your specification if you need fixed voltage, what output current you need, and then you have to make your calculation based on that. I have already provided a document. I will put it in the you learn how to make all this calculation for this specific case. Then I have here the typical schematic from our buck converter datasheet. I just put it here to show you. And as we saw in the schematic, when we're changing the Vin or the Vout, always this inductor changed, inductor value changed, and the rest stay the same basically. Of course, R1, R2, it will change depending on the Vout. So if we start from C1, which is recommended here. So this capacitor main job is to supply the sharp pulse of current that cover draws with every switching cycle. So by providing this current locally to the Vn, it keeps the voltage at the IC stable and prevent the dropout voltage. And we should keep the C1 as close as the Vn. Then for C2, it's the main job of this C2 is to catch the very fast switching spikes, which they are normally in nanosecond. So if we have a tiny value like 100 NF, that will lead, we will have low ESL and ESR, which lowers the impedance at high frequency. Also, the placement it should be close to the Vn. Then we have this C3. So in this specific buck converter, it's provide floating gate drives. So the high side MOSFET has a stable VGS, so voltage gate to source during its own time. Then we have C4 and C5. So those are the output capacitor. It smooths the output and the power coming from the inductor to give our load a clean, stable 3.3. And I'm using here, you can see I'm using 222 micro on parallel. So basically, instead of using LC filter, I'm using LCC filter. And using those two capacitors give us better performance. It lowers the output voltage ripple even more and help the circuit to respond better to sudden change in the load current. And that's what we call it transient response. Then we have the two the two capacitor here, which I get the value from here. If I need 3.3, then R1 should be 75 kilo ohm, and then R2 should be 24 kilo ohm. So in our layout, now you can see we have one loop here, and then we have one loop here, and then we have the feedback loop here to the ground, and then we have the SW loop, which going to the inductor, two capacitors, and then to the ground. So that's it about the schematic. Thanks.